Welcome to Brain Vision.
In this exercise, we're given the information that the energy level Zn of one electron atoms and ions is given by minus mu k squared q1 squared times q2 squared divided by 2 h bar squared n squared. Okay, where mu is the reduced mass, that's equal to the mass of the electron, m1 times the mass of the nucleus, m2 divided by m1 plus m2. q1 is the charge of the electron and q2 is the charge of the nucleus. And we are also given the information that when the hydrogen atom transitions from the state n equals 3 to the state n equals 2, it emits a photon whose wavelength, lambda h, is equal to 656.2 nanometers. And based on these informations, we are asked in question A to calculate what is the wavelength emitted by the positronium, which I'm going to call lambda p. Remember that the positronium consists of an electron that orbits a positron. And in question B, we have to calculate the wavelength lambda that will be produced by an ionized helium atom. Okay, and in both situations, we have to consider that the transition that the atom-like object undergoes is from the third energy level to the second one. So it's from n equals 3 to n equals 2. Okay, so let's solve question A. First of all, let's calculate what is the reduced mass of the positronium. So we know that the reduced mass is the mass of the electron m times the mass of the positron, which is the same as the mass of the electron, so it's m squared, divided by the mass of the electron m plus the mass of the positronium, which is also m. So the reduced mass is m over 2. That's the reduced mass of the positronium. Okay, notice that the energy of the hydrogen atom, I'm gonna leave the h here to explicit that it's the hydrogen atom, in the nth energy level is given by minus the mass of the electron, because the reduced mass of the hydrogen atom is just the mass of the electron, times k squared q1 squared, which is just the charge of the electron, times the charge of the proton, which is also e, and that's squared, so it's e to the fourth, divided by 2 n squared h bar squared. Okay, that's the energy of the hydrogen atom. Now, the energy of the positronium is given by minus the reduced mass, which is m over 2, times k squared, times the charge of the electron squared times the charge of the positronium squared, and the charge of the positronium is equal to the charge of the electron, so this is e to the fourth as well, divided by 2 n squared divided by times h bar squared. So notice that this is the same energy as the hydrogen atom, but divided by 2. Okay, so I have that the energy of the positronium, EPN, is equal to the energy of the hydrogen atom, EHN, divided by 2. Okay, and we have the information that the hydrogen atom emits a photon that has a wavelength 656.2 nanometers. Now remember that the energy of a photon is given by hc over lambda. Okay, so if the energy of the photon is proportional to the energy of the energy levels of the hydrogen atom. Okay, so if the energy of the energy levels of the positronium are half the energy of the energy levels of the hydrogen, then the wavelength lambda will be 2 times the wavelength lambda of the positronium will be 2 times the wavelength of the hydrogen atom. Okay, that's created by the hydrogen atom. Okay, because the energy is proportional to 1 over lambda. So from here, we can get that the wavelength of the positronium is 2 times 656.2 nanometers. So the wavelength of the positronium is 1312.6 nanometers. Okay, and in question B, we have to calculate the wavelength of the light that's emitted by the helium, the ionized helium ion. And what we have to do there is to notice that the energy of the helium is given by minus m, because the reduced mass of the helium is just the mass of the electron. Okay, because it's the mass of the helium, the mass of the electron is much smaller than the mass of the proton. Okay, so this is just the mass of the electron times k squared times the charge of the electron squared, which is E squared, times the charge of the nucleus squared. And the charge of the nucleus of the helium is 2e, so the charge of the nucleus squared will be 4e squared divided by 2h squared n squared. And notice that this is 4 times the energy of the hydrogen. Okay, so if the energy of the hydrogen atom is if the energy of the helium atom is 4 times the energy of the hydrogen atom, then the wavelength produced by the helium atom is 1/4 the wavelength produced by the hydrogen atom. Okay, so this is 1/4 of 656.2, which is 164.1 nanometers. And this is the wavelength produced by the helium atom.